In this video, we're going to be studying rolling scenarios. So we're still going to be using the same principles of rotational dynamics using the net torque equals I alpha, but we'll talk about rolling without slipping and mostly do it through the forces analysis. In the energy unit, we'll be talking about how to do it from an energy point of view. So this will be mostly looking at the frictional forces, how we go about applying them, when do they apply, what's the direction of the force, and solving several rolling problems. The last part we're going to talk about here is an application of dynamics, which is rolling down inclines or rolling in general. We'll revisit this when we do work in energy as well, but when objects are rolling, they may be slipping or not slipping. This is an important distinction to understand. And so slipping motion is the object is rubbing against the surface, and non-slipping is not rubbing against the surface, or it's static friction. So let me kind of show you. This one's a little bit tricky. So when we're rolling without slipping, it's rolling in such a way that this surface is not rubbing against my skin. It's rolling on that surface, and it just rotates it just the right way so that it's not rubbing. Whereas this would be rolling, if it were rolling and slipping, it's rubbing against my surface. And so that's kinetic friction versus rolling without slipping, which may or may not be static friction. Okay, and so the distinction between them is whether or not it's rubbing against the surface. And that's why we use that as a rule of thumb to identify whether it's kinetic. Both cases, we're moving. That's why kinetic friction is not about whether an object moves. It's about whether it rubs against the surface. Okay, so be careful. Rolling can have either kinetic friction or static friction depending on the kind of rolling that's happening there, whether it's rubbing against the surface or not. Okay, so let's talk about rolling without slipping. So when an object is rolling without slipping, then there's a key relationship between the center of mass and the angular velocity. It's the center of mass equals r omega. And that's important because it means it's the reason that occurs is because the relative velocity. Now, you want to be careful. We've had this v equals r omega before, but this before referred to the fact that when you are rotating something and you want to relate it to the linear speed at the end of something that was spinning, right? We wanted to relate those two. So it looks like the same formula, but it has a very, very different meaning. And so let's talk about it. So let's say I'm rolling along a surface here. I'm rolling without slipping with an angular velocity v. And that means the center of mass is moving with a velocity of center mass here. Now, because we're not rubbing at the surface, what we need to think of is that at this point, the velocity needs to be 0 at that point. Why? Because it cannot rub against the surface. So right at that point, the velocity needs to be 0. There are two components of the velocity that are happening. One, the entire thing is rolling to the right. So that means the velocity of the center of mass is acting going to the right as well. But also it's spinning. So that means there's some tangential velocity from the v spin. And we want them to cancel each other out because if we're rolling without slipping, then the net velocity needs to be 0 at that point. That means the velocity of the center of mass has to equal the velocity of the spin, which is equal to the r omega. So important, this is only true when we're rolling without slipping. If we're rolling while slipping, this is not true anymore. So this is a condition for it. And you can have a similar thing for the acceleration of center mass. It's r times the angular acceleration. Again, not something we usually do as much. Usually we handle this case. But the reason being is because right at that point, the velocity does need to be 0 because it's not rubbing against the surface. An important note is friction. We'll talk about when we do torques. We'll talk about the next part here. So let's go through an example here. We have a marble with a mass m and radius r, starts at rest and rolls without slipping, rolling down an incline. So mass m and r, angle 30 degrees. It's rolling without slipping down an incline. What is its acceleration? Okay, so you might think like, isn't it just g sine theta? A lot of people do inclined planes, they say it's g sine theta. Now, we have to keep in mind something. One, we did not say it was frictionless. Now, why would there need to be friction here? And this is an important part of the rolling because there is an angular acceleration, right? Because it's going to start at rest and then it's going to start spinning clockwise. So there's an angular acceleration this way to cause it to accelerate its angular speed down the ramp, right? And so if there's an angular acceleration, there has to be a torque. Let's start with our positional free body diagram. We're going to have mg here, and then we're going to have a normal force right at the surface there. And let's say those are the only forces. So if I look at my axis of rotation right here, okay, mg is not going to exert a torque because the r is 0. And remember, this thing's going to be spinning around its center of mass as it's going down. And if you look at the normal force, you're like, is the normal force exerting a torque? Well, no, because if you draw the r vector from there to there, there's no component of the normal force that's perpendicular to the r vector. So the normal force that can't exert a torque. Remember, a torque requires a force component to be perpendicular. If it's parallel, like this case, the normal force is parallel to my r vector, that means that the torque is going to be 0. So there must be something else that causes a torque, and in this case, it's actually going to be friction. That's the only thing in contact that could possibly do anything. Now, it's static friction in this case. Now, which way is the friction going? I have it pointing up the ramp. There's a couple of ways we think about this. Remember, with static friction, there's 2 ways to think about the direction of it. Always a tricky scenario. One is, if there were no friction, then it would just slide down the ramp. And which direction would the friction want to act? Up the ramp, just like kinetic friction. Because if there are no friction, it would just slide down the ramp. So that's one way to think of it. The other thing is we need a clockwise torque. And the only way to get a clockwise torque is if the friction's pointing, is if the friction's this way. That direction would cause the object to rotate clockwise. So both of those cases tell us that the static friction have to be in this direction. Okay. Now we can do F net equals ma and net torque equals I alpha. Let's do the net torque equals I alpha first, because you might think that might be easier. Well, the only torque is from the force of friction. The r vector is r, so it's going to be r times force of friction is equal to I, and that's the positive direction. And we'll make this the way the positive direction. Is going to equal I, which is 2/5 mr squared times alpha. So the one of the r's cancels, so you get the frictional force is equal to 2/5 mr alpha. Now, the r times the alpha, because it's rolling without slipping, this is just equal to whatever the acceleration is. So this is 2/5 ma. Unfortunately, I don't know the frictional force, and the coefficient of friction, by the way, wouldn't help because this is static friction. So now we're going to look at F net equals ma, because that is also true. So if we make down the positive direction, this way the positive direction, what do we got to do with our forces? Well, we got to decompose mg into mg sine 30 degrees and mg cosine 30 degrees, but I only care about the force down the ramp because that's the acceleration. So mg sine 30 degrees is down the ramp, so it's positive. Force of friction is up the ramp, so it's negative, and that's equal to mass times the acceleration, right? This is our unit 2 stuff. Hopefully that part, you should be solid point at this point. But now we see like, oh, now I can use this frictional force to plug in over to here. Minus 2/5 ma is equal to ma. We can add those over. So mg sine 30 degrees is going to equal 2/5 plus 1, which is 7/5 ma. Because you have 2/5 ma plus an ma. Then the m's will cancel. And then the acceleration is going to be 5/7 g sine 30 degrees. Notice that this is less than a normal inclined plane, which is just g sine theta. And that's because there's some friction going up the ramp. It's not going to go as fast as something that slides down the ramp. What's the speed of the marble at the bottom of the ramp? How fast are we going down here? Well, now we can use kinematics. Because could we use energy? We haven't talked about rotational energy, so we cannot use energy yet. We can just simply use kinematics to say we know this height is h. We know the distance we want, because now we know the acceleration, so it's just the kinematics, right? We just say down's the positive direction. We start at 0. The acceleration is 5/7 g sine 30 degrees. We want to know the final velocity. I either need to know how long it takes or I need to know how far I traveled. Well, we had an initial height h. That means if from a right triangle, if this is h, we know that this distance that we're going to travel, we know that h is equal to d sine, or think of it as opposite over hypotenuse. Sine of 30 degrees is going to equal h over d, opposite over hypotenuse. Therefore, the d is equal to h over sine 30 degrees. So how far we're going to travel is h over sine 30 degrees. And we can have our answer in terms of h because that's something they gave us already. So then what kinematic equation are we going to use here? V squared is v naught squared plus 2a delta x. So this is going to be v is a square root. That's just 0. 2 times a, which is 5/7 g sine 30 degrees times delta x, which is h over sine 30 degrees. Turns out the sine 30 degrees doesn't matter. So this is going to be square root of 10/7 gh. That's how fast we're moving down the ramp. Now, there's a way to do that with energy, but we'll talk about that in the next unit there. If you found this video helpful, come check out our school community. It's got an amazing bunch of features. It's got extra videos, corrected videos, better than the ones that I have errors on YouTube. It's got multiple choice free response questions. I hold live Q&A sessions and go through more problems and I answer students' questions, help with schoolwork, all kinds of things. If you want to check it out, look in the description below or check out the website and find us in the school community. You get a 7-day free trial to give it a shot, just to check it out, see what it's like, come join some calls, and honestly, come learn AP Physics 1 even faster with us.